Follow up to the previous question, we're going to do some application on the probabilities. We're going to start with the probability of an Deca card where you're going to get a queen followed by a queen. So as a reminder to everybody, a Deca card is made of um, 52, 52 cards. Okay, so not 52 cards, and these are split into four types of cards. You have the heart, you have the diamond, you have the spade, and you have the club. Okay, and you got from 2 all the way up to 10. You also have the ace, which is number 1, so this is the ace. You have the valet, you have the queen, and you have the king, and that's got to be repeated in every one of the situations. Okay, so let's go back to our problem. The problem says if you have a Deca card, so you have Deca card, and you're going to take 2 cards. Okay, and the question is, what's the probability that you're going to get a queen, and then you're also going to get a queen? So the way we do this is we're going to think about it the way we learned about probability. So probability of a queen and a queen is actually the probability of a queen on the first, and so actually it's a multiplication, the probability of a queen on the second, given that it was a queen on the first. If you're asking yourself, where did I get this? This is the probability of A and B, which is equal to the probability of A times the probability of B given A. Okay, so in this situation, A is nothing but queen on the first. Oops, I don't know how I did that. Let me fix that a second. Okay, got it. So this is what I was saying. I was saying that A is nothing but the probability of the queen at the first trial, and B is the probability of the queen on the second trial. Okay, so that's you get the probability of A, which the probability as the first card being a queen, and then probability of B given A, which is the probability of a queen on the second one, given that the first one occurred. Okay, so if we know that, then the rest should be easy. Let's see if we can get this probability done correctly. Okay. So what's the probability of getting a queen on the first time? Remember نحن قلنا it's success over all possibilities. So you start off having 4 queens and you have 52 cards. So that's the first one, easy. Then you're going to multiply by getting again a queen on the second time. However, knowing that you already got a queen the first time, so it means that you're only left with 3 queens and 51 cards. And therefore, that's the answer for the first application we had over here. Show the probability of getting a queen and a queen. Okay? Right. Let's look at the second one. What's the probability of only 1 queen in 2 cards? Okay. So now we're back at taking 2 cards, but we want to know show the probability that I'm going to get only 1 queen. So when something like this happen, or anytime you are actually calculating a probability, you have to ask yourself, how can I get a queen and not a queen? How can this happen? And what I mean here is actually the order. And it turns out that there are 2 possible ways this can happen. You can start with a queen, followed by not a queen, or you can start with a non-queen, followed by a queen. And notice I said or. So this is going to get a probability and that is going to get you another probability. And since we said or, it means that this is an additional probability. So remember, probability of A or B is the probability of A plus the probability of B minus the probability of A and B. Okay. In the event where this is actually 0 because there is no intersection, then this is your probability. So the intersection in this scenario would mean that the first one is a queen and the second one is a queen, which is not possible because we're only looking for the probability of one queen. So actually there's no interaction between these two. So you end up calculating the probability of a queen followed by not a queen. Then you calculate the probability of not a queen followed by a queen, and then you're going to add up these two together. Okay, so show the probability of a queen followed by not a queen. So the probability of getting queen on the first one is 4 over 52 because you have 4 queens and you have 52 cards, and then you're going to multiply by, now you're going to get not a queen. So how many not queens do we have? We have 48 cards that are not queens, but you're going to divide by 51. Why we're dividing by 51? Because the first card has already been drawn. So you have one card that already was taken out. You're left with 51 cards. This goes back to what we said early on, that the probability of a queen and then a queen, well, not a queen, it doesn't matter. This is where it's the probability of a queen in the first times the probability of a queen in the second, followed by a queen, given that the queen is in the first. Okay, so that's where this is coming from. Alright, so that takes us to the second one. Show the probability of the first card being not a queen. Okay, we know we have 48 that are not queens divided by 52 cards. And then you're going to multiply by whatever is the second one, which is now you want to get queens. I know you're left with 4 queens, and you multiply by 51. Okay, so what you hopefully noticed by doing this exercise is that it turns out that this and this are exactly the same. So when you add up together, you can just multiply by 2. So you can say 2 times 4 times 48 divided by 52 times 51. That is the answer for the probability we're looking for. Okay, and if we go back to the example, we did a queen and a queen. Then we did only one queen and 2 cards. So you're taking 2 queens and only one of them. You're taking 2 cards and only one of them is a queen, and therefore you have to account for the order. It could be the first one is the queen, or it could be the second one is a queen, and then therefore you have to calculate both. The last example is, what is the probability that both cards are not queens? Okay, so we go back to our drawing board. Okay, let's see if we can get it right. So it's the probability of not a queen and not a queen. Okay, so we know this is the probability of not a queen on the first. So this one stands, and that's the first card, multiplied by the probability of not a queen on the second, provided that the first card was not a queen. Okay, so show the probability if you were to draw one card, it's not a queen. We know that you have 48 cards that are not queen. You divide by the total number of cards, which is 52. So that's the first one. Now for the second one, you also want not a queen, but how many not queens are left out? 47, because the first one was already drawn, and you divide by 51, and you're done. Mafi order. This can happen only one way. Not queen, not queen. That's it. Okay. So when we did the queen, can be only one way this can happen. If you do not a queen and not a queen, this also there's only one way this can happen. However, when we do queen and not a queen, بما إنه it can be the other way around as well. So you have to account that there are two ways this can happen. Okay? And if everything was done correctly, then adding up these, sorry, I did the exact same thing I did it a minute ago. Okay. So if you do it correctly, this means that these three together are going to add up to 1. Okay? لأنه هول الثلاثة, these three probabilities are actually complement. مع بعضهم they're complement. So if you know two of them, you can find the third one. Alright? Okay, so that concludes the example working with Deca cards. Let's see what else do we get. Okay, what is the probability that if you toss two coins, you get both of them are heads, both are not head, and only one is a head? So, come in, the same idea. But this time we're working with tossing coins. So if you're tossing coins, and you know that when you toss a coin, there is only two possibilities, right? When you toss a coin, it's either head or tail. ما في شيء تاني. Okay, so here we're tossing two coins or one coin twice. It doesn't matter. There are possibility that you can get a head and a head. There's a possibility that you get not a head and not a head. And there is a possibility where you're going to get one head only. Okay? Now, the thing about not only one head is that this can happen in two ways. Right? It could be head followed by not head. And in this example, it would be tail. Or it could be not a head followed by head. So you have to do both of these to get this one. So let's calculate the probability. Show probability of head followed by a head. So it's the probability of a head on the first times the probability of a head on the second, given that the first one was a head. Okay? Now show the probability that you get a head in the first toss. This is actually 1 over 2. There's only two possibilities, head to tail. And then you're going to multiply that by the probability of, what's the probability that you get ahead on the second one, knowing that you get ahead on the first one? Well, it doesn't matter, it doesn't change, but dalla 1 over 2. Okay, so in that scenario that I just mentioned here, when this probability is exactly as this probability, this is when we talked about the probability of A given B is actually so that's we talked about the probability of A given B equal the probability of A. إن ساعتها A and B are independent, which is the first toss and the second toss are independent. The probability doesn't change. And therefore the probability of getting a head and a head is just 1 over 2 times 1 over 2. نفس الشيء for the probability of not a head and not a head. It is actually 1 over 2 times 1 over 2. And then the last one, which is head followed by not a head, that's 1 over 2 times 1 over 2. But it can happen in two different ways, so you have to multiply it by 2. Okay? So let's wrap up things. The first one gave us a total probability of 1 over 4. The second one gave us a probability of 1 over 4 as well. The last one, these cancels out, so you're left with 1 over 2. And you notice that if you add these three probabilities together, you're going to get 1, because these are complement to one another. يعني this is everything that can happen when you toss a coin twice. ما في شيء غير إلا هول. Okay. So these are the applications with coins and with the Deca card for the probabilities. استعملنا ال additive rule وال multiplicative rule. Also using the conditional probabilities, and we looked at things when they are independent. More example. What's the probability that if you have a pin made of 4 digits, that somebody would be able to guess your pin number, knowing that they get to have 3 trials? Okay, so we're back here, and this is your pin. It's made of 4 digits, and we are wondering شو probability that someone can guess your pin number, given that they are given 3 trials. Okay, all right. So think about it. If somebody is given 3 trials, how could they? What can happen? Well, they could guess it from the first trial, or from the second trial, or from the third trial. وطبعا في the last one, which is not guessing it at all. So our job is to calculate the probability of guessing from the first, second, third, and then since we said or, we need to add these 3 together. There's no intersection between them, because if you guessed it in the first time, you're not going to guess in the second time. And if you guessed it in the second time, you did not guess in the first time. Okay, so they are mutually exclusive. We get these probabilities, and we add them up. You get the probability of somebody guessing your pin if they're given 3 trials. All right, to be able to do that, we have to think about how many possibilities, how many combinations of pin number made of 4 exists. Well, you can go from 0, 0, 0, 0, that's the lowest value of a pin value, all the way to 9,999, okay, with everything in between, and that gets you 10,000. Another way to think about it is that the first digit can be filled anywhere between 0 to 10, 0 to 9 I mean, so that's 10 possibilities. The second one also between 0 and 10, so that's another 10 possibilities. The third one also 10 possibilities, and the last one is also 10. So you get 10 times 10 times 10 times 10. That is also 10,000. So both approaches gets you to the conclusion that there are 10,000 possibilities. There are 10,000 possibilities. Okay, how many of these 10 possibilities is your actual pin code? Only one of them. Okay, so عندنا واحد بس اللي هو success. Therefore, the probability of guessing at the first trial is the right one over all the possibilities, which are 10,000. This is guessing the first time. Guessing in the second time, it means that the first time you guessed wrong, and the second time you guessed right. So you started with wrong on the first one and the correct at the second time. So show probability of guessing wrong the first time. We know there are 9,999 wrong over 10,000. This is the probability of guessing wrong the first time, multiplied by guessing right in the second time, which is there's only one right, divided by, well, hopefully he's not going to or she's not going to repeat the first code, so the 10,000 codes are now dropped by 1. So now I have 9,999 different codes to choose from, and you notice that I can simplify, and I'm back to 1 over 10,000. And it turns out it's even true for the third trial. So it's wrong the second time, and correct the last one. So wrong the first time, we already calculated that. That's 9,999 over the 10,000. Again, wrong the second time. Well, this time the wrongs have dropped by 1, so it's 9,998. And the total have dropped by 1, so it's 9,999. They dropped by 1 because he's not going to repeat one of the codes that he already or she already tried. And now the last one is correct. So now it's the correct one, which is 1 over how many possibilities left? 9,998. Okay? And again, you can simplify this by this by that, and again, you're left by 1 over 10,000. So it turns out the probability of guessing the first time is exactly as the probability of guessing the second time, which is exactly equal to the probability of guessing the third time. And since whoever is trying your pin code get to have 3 trials, then it's 1 over 10,000, 1 over 10,000, 1 over 10,000, and the last, so the answer is 3 divided by 10,000. That's the probability of somebody guessing your PIN code if you have a PIN code of 4 digits made of only numbers and they get to try 3 times. Obviously, that's a very, very low probability. So it's very unlikely. So going back to what I discussed in the previous lecture, then when the probability gets to 0 or very close to 0, that means this is very unlikely to occur. And therefore, if for some reason somebody was able to get a hold of your credit card and they were able to withdraw money, and given the two possibilities, the two options, either they they do not know you and so they guessed because they do not know you, and that is the probability of that, or they know you and they know your PIN code, so that's somebody that knows you and somebody that knows your PIN code because maybe you gave them their PIN code. It could be a friend or it could be a family member, so they took your credit card and bought something and they know, so the probability of that is actually 99,997 over 10,000. So the probability of that is 99.97%. Okay, so that means that somebody stealing your credit card and guessing it just by chance, the probability of that is very, very, very tiny. The probability that they actually knew your PIN code is very, very large, and we are leaning towards believing this more than believing that. Okay. Okay, so we're carrying with the application for probabilities, and that takes us to something that we discussed, which is the diagnostic test, introducing the concept of sensitivity of a diagnostic test, which is the probability of testing positive giving the disease, the specificity, which is testing negative giving healthy, no disease. Okay, and in that scenario, I'm giving you a probability of disease to be 40%, and then I'm saying, okay, if you have 1,000, let's fill out the table and let's try to calculate the positive predicted value, negative predicted value. Let's do that one step at a time. Basically, when we have a diagnostic test, the way I set it up is I create a table that looks like this. Okay, you've seen this. This is a contingency table, a two-way contingency table. On one end is the disease status, so either diseased or not diseased. On the other hand, I'm going to put the test result, so it's either testing positive or testing negative. We have been told that 1,000 people, so the total is 1,000. We're also told, based on here, that the probability of disease is 0.4, and 40% of the sample have the disease. Okay. If probability of disease is 40%, that's all of those that have the disease divided by the 1,000, right? So all those that have the disease, meaning all those that have the disease, the number here. So hopefully you can figure out that this number is actually 400, because 400 over 1000 gets you the 0.4. Okay? Alright, so if you know that 400 have the disease, it becomes pretty much clear that those that do not have the disease are actually 600. Obviously, these two numbers should add up to 1000. Let's continue with what we're given. We're told that the sensitivity is equal to 0.9, the specificity is 0.8. So the sensitivity is nothing but the probability of testing positive given that they have the disease, and this is equal to 0.9. Alright, so given the disease, so we're only going to look at those, yani those that the 400. Positive is 90%, yani 90% of the 400 are going to test positive. So what is 90% of 400? Well, it's 400 times 0.9, yani it's 360. And that means you're left out with 40 here. Okay, 360 plus 40 is 400. The second value we're given is the specificity, which is the probability of testing negative given not diseased, and we're told this is equal to 0.8. That means given not disease, we're looking at the yellow people here, or the yellow number I should say, and that we're saying that 80% of these 600 are testing negative, and I should put them here. So what is 80% of 600? So I multiply 0.8 by 600, and that should give me 480. And therefore 480 plus something is equal to 600. Obviously this is 120. Okay. Now I can carry and I can go ahead and add up the marginals. So if I want to figure out the total of positive, and it's 360 plus 120, so that's 480 in total tested positive, and the total that tested negative 40 plus 480, that's 520, and obviously 480 plus 520 is equal to 1000. Now that this is done, I can go ahead and calculate the things that they asked me for. They asked me should a probability, this is called the positive predicted value, which is the probability of actually having the disease if you tested positive. This is a conditional probability. So remember, anytime you're working with a condition, you stick to the condition. So we're only going to look at those that tested positive. So my denominator is the 480. And now out of those, the question is how many actually have the disease? This is the success, the disease. It's only 360. And 360 divided by 480. Let me calculate that. I'll be right back. So it turns out this is equal to 0.75, yani 75%. So the difference between this, which is the positive predicted value, and this, which is sensitivity, this means that the test, so it's positive given the disease. Given you have the disease, 80%, no, for 90%, you're going to test positive. So this is the capacity of the disease to actually capture the capacity of the test to capture those and label them as positive. Okay, so if you walk in and you actually have the disease, 90% chance you're going to test positive. However, the positive predicted value is you tested positive, what are the chances that you actually have the disease? So somebody who tested positive, 75% chance that they actually have the disease, which means 25% chance they do not have the disease. And similarly في عنا شيء اسمه negative predicted value, and this is where it's still a probability that you are healthy if in fact you tested negative. So the condition is testing negative, so we're going to only look at those that tested negative. So I'm going to divide by 520, and the success here is being healthy, which is 480. So 480 divided by 520, the answer to that is 92.3. So 0.923. That's a 92.3%. Okay, so what does that mean? Again, let's compare the negative predicted value to this. This is what we call specificity of the disease. So this test, specificity of the test, I'm sorry. Specificity that this test is capable of correctly labeling 80% of the healthy. So out of all the healthy, 80% end up being negative, okay? Whereas the negative predicted value, you're looking at it this way. So if you take the test and you're actually your test is negative, then there's 92.3% chance that you're actually healthy. Meaning there's still 7.7% chance that you're actually diseased. Okay? So that's the difference between what is known as um, uh, sensitivity of a test, specificity of a test, positive predicted value, negative predicted values. So I'm going to show you an application which is coming from the real world. So the example we're going to look at is an example coming from the OBGYN or pregnancy and diabetes. During the second trimester, a pregnant woman might get something called gestational diabetes, and it's very important that to be detected. So the hypothetical scenario is the following. Let's say in a certain clinic over a year, 5,000 women, pregnant women, are tested for the gestational diabetes using test number 1. Okay. Now, one thing that you have to know is that the probability of gestational diabetes, so disease and healthy, as we said earlier, and the test could be positive or negative. The thing about gestational diabetes, the disease, it's that it occurs only in 5% of the cases. Okay? And test number 1 is going to have a sensitivity, yani probability of testing positive given if the woman has the disease, which is equal to 90%. And it's going to have a specificity, which is the probability of testing negative if the woman is actually healthy, which is going to be equal to كمان حنقول 90%. Okay? Okay, now look what's going to happen. So first of all, as we did in the previous example, we're going to figure out how many total women with the disease we're going to get. It's 5%. So if you calculate 5% out of the total, اللي هني 5,000 women, that is going to be up to 250. And that is going to leave you with 4,700, 250 as healthy. Okay? I'm sorry, I wrote it a bit wrong. Let me clean that. Okay. So 4,750. Okay. Now, next thing we want to do is we're going to try and put the values inside the cells. Since sensitivity is 90%, yani 90% of the 250 are going to be labeled positive. 90% of 250 is actually 225. Okay. And you're left with 25 that you missed them. And also the specificity of the test is 90%. يعني 90% of the healthy are going to test negative هون تحت. And 90% of 4,750 is 4,275. And that leaves you with 475 actually testing positive. Okay, مع إنه هن they're healthy. Now, if you come and you calculate the total positive and the total negative, the total positive comes out to be equal to 700, and the total negative comes out to 4,300. Okay. Now, let's think about it from the perspective of the patient or from the doctor's perspective. The doctor or the patient wants to know that what are my chances if I actually tested positive? What are my chances that I'm actually diseased? And if I tested negative, what are my chances that I'm actually healthy? Yani holy, that's what we call the positive predicted value and the negative predicted value. So the positive predicted value, the PPV, which is the probability that the woman actually has diabetes if she tested positive, and the negative predicted value, that's the probability of the woman being actually healthy, okay, if she actually tested negative. All right, so for the first one, so it's a conditional probability looking at only those that tested positive. So looking at only the 700. Out of the 700, how many actually have the disease? And this is 225 divided by 700. And the answer to that is actually 0.3214. So I'm going to stop at the second digits. And only 32%. What is the probability if the woman tested negative that she's actually healthy? So I'm going to only look at those. Okay. So my total is 4,300. And how many are actually healthy? That's the 4,275. And if you do the calculation, you're going to get 0.994. So what does that mean? Well, it means that after the test is done, if a woman tested negative, 99.4% she's healthy, so we feel comfortable telling her, fine, go home. However, if a woman tested positive using this test, if she tested positive, there is only 32% chance that she actually has the disease. Yani, actually, there is more chances, double the chances that she actually is healthy. So testing positive on this test doesn't really help us. Actually مثل ما قلنا في twice as much chance of her being healthy than actually being diseased. So physicians at this stage do not initiate medication. What they do is they say we need a follow-up testing. We need to do a second testing. But this second testing is going to be done not on the 5,000 women, because as we said a minute ago, these 4,300, we feel pretty comfortable that they are healthy, so we send them home. We're only going to repeat, or we're only going to do a follow-up test on these 700 women. So we take these 700 women, and they now are going to become the new sample where we're going to run the new test. So now my new total is 700, okay? And diseased and healthy, testing positive, testing negative. So I know that out of the 700, 225 henni, those that actually have the disease, and 475 henni healthy. Okay? But this new test, this test number 2, is not the same as test number 1. Test number 2 has a different sensitivity and a different specificity. Okay, so now I'm going to change the specificity and the sensitivity. The specificity for this test, so the excuse me, I should have said sensitivity. I'm going to start with sensitivity. اللي هي هون, you can see that. Gain it 90% for this test. For that test, I'm going to pick it as 96%. And for specificity, for the new test, which used to be كمان 90% for test 91 for test number 1 is going to be 92%. Okay, so using the same rationale in filling up this table, I'm going to use to fill out this table. So what is 96% out of 225? Okay, because that's what sensitivity is. You take everybody that has the disease, and out of that, you take out 96%, you put them in the positive, and 4% you put them in the negative. So do your calculation, multiply 225 with 0.96, you should get 216, and you're left with 9 in the negative. Okay, now let's do the specificity. 92% of the 475 are going to be negative, and 8% are going to be positive. Okay, if we do your calculation, you're going to find that 437 are going to be negative, and 38 are going to be testing positive. Now let's again get the marginals. So 216 plus 38, that's 254 total positive, and 446 total negative. هلا on this follow-up test, we're going to calculate again the positive predicted value and the negative predicted value. So the positive predicted value is out of everybody that tested positive, how many actually have the disease? So divide, my total now is 254, and actually 216 have the disease, and that gives you 85%, 0.85. For the negative predicted value, out of everybody that tested negative, the 446, طبعا صرنا عم نحكي على second round of testing, how many actually are healthy? That's 437, and this is 97 point, so it's about 98%, 0.98. Yani, what that means is that after we finished the first round of testing, and we said to 4,300 women you can go home, for the 700 that tested positive, we told them we need you to come back for another testing. So these 700 women come for another testing. We have them take another test. And now, if a woman on the second testing tested negative, I'm 98% sure that she's healthy. However, if on the second test she tested positive, I'm 85% sure that she has the disease. I was able to improve my my senses of how much a test positive is actually mean that somebody has that gestational diabetes from 32% to 85%. Okay, so basically this is what happens a lot of times. You run the first run of test, and then by looking at the negative predicted value and the positive predicted value, when one of them is very low, it means that you cannot trust it. So هون كان عندنا given positive was very low, and therefore we repeat for the positive. If the negative predicted value was the one that was very low, we would have repeated for those that tested negative. So we take those that tested either positive or negative depending on the result. In our case, we took those that tested positive, and we had them repeat using a different test. Sometimes you can use the same test. So have them again, and this time the way you allocate the numbers is using the 90%, 90%. That means that you're using the same test. Or you can change the test and use a different test with different sensitivity and different specificity. Okay, and by doing a second test, you can recalculate the positive predicted value and the negative predicted value, and now you can have a better sense of who has the disease and who doesn't have the disease. Okay, so that would conclude our application on probability using contingency tables, using the formula for the cards, tossing the coins, etc. And let me just do one last thing. I just want to show you شو معناتها independent. If two two elements are independent. How can you see that in the contingency table? All right, so if I'm looking at the contingency table and I'm looking at uh, who is getting an A on the course and who's not getting an A on the course, and I'm comparing the female student to the male student, and let's suppose that I have 200 female students and 50 male students. Okay, and it turns out that out of the 200 female students, 20 got A and 180 got not A. And out of the 50 male students, 5 got A and 45 did not get an A. Okay, so the total of A is 25, the total of not A is 225, and the total is 250. Here's an example where the grade and gender are independent. How? Well, you can calculate the probability of A. You can calculate the probability of A given she's a female student, and you can calculate the probability of A given he's a male student, and all of these are going to be exactly the same. Okay, if you do the calculation, they're going to be exactly the same, meaning getting A has nothing to do with your gender. Okay, it's independent of your gender. So 10% of females get A, and 10% of male gets A, and 10% of everybody gets A. So بنقول gender and grade are independent. مش mutually exclusive, obviously, because you can see that there is a crossing between them. Okay? Mutually exclusive would be if none of the female gets A. If you get a 0 here, for example, that would be mutually exclusive. However, it's not. We have a crossing. We have a joint cells that have both at the same time, an intersection. We do have an intersection. But the probability of the conditional probability, the conditional probability of A given female or A given male is the same, which is also equal to the probability of A. So it doesn't change. هون بنقول independent. Okay? However, if the values actually were not like that, so if, for example, نقول the probability of getting an A for female was, let's say, 20%. Okay, that also automatically is going to change here, the total here. Now recalculate these probabilities. So this is now 45, and this is 205. Now calculate this and this and that, and you will see they're not equal. And therefore, we can say, in that scenario, we can say that gender and grades are dependent. They are dependent. Okay? So that's an example of independent and dependent. And that concludes the lecture. Thank you so much for your time.